talk about deviations from ideal gas behavior. And so this means we're talking about real gases. And the point of the section is really just to help you understand that gases do not always behave ideally. There are certain conditions for which gases do not behave ideally, and the ideal gas law breaks down. Let's think about the ideal gas assumptions. So what makes an ideal gas ideal is the fact that you can neglect its volume relative to the volume in which the molecules are moving. Okay, so molecular volume is negligible. And then you can also neglect the interactions between molecules. And the reason for that is the molecules are so far apart in a gas. Okay, so they rarely come into contact except for when they collide. And then when they collide with one another, it's more or less an elastic collision. So that means there's no attractive or repulsive interactions between the molecules. That is generally true when the pressure is low. Okay, so for low pressure conditions and large temperature, the ideal limit, the ideal gas law is satisfied. And so we call this the ideal limit. Low pressures, high temperatures. You can also discuss this in terms of a large molar volume or a low density. These are all different ways of saying low pressure. So the ideal limit means low pressure conditions. However, as you start to increase the gas pressure, you're going to start squeezing the molecules closer and closer together. The molecular volume is going to become more important. It's not going to be as easy to neglect. Likewise, you won't be able to neglect the interactions between molecules once the pressure gets high enough. They're going to start to feel attractive and repulsive interactions. One way to quantify whether or not a gas is behaving ideally is through something called the compressibility factor. And you're going to have to forgive me that I have an error on this slide. I've defined the compressibility factor incorrectly. It should be defined as Z equals P times Vm divided by RT, where Vm is the molar volume. It's the volume per moles of gas. And then we are to take these quantities as the real quantities. So this would be the real gas pressure, the real gas volume, the real gas temperature. Now, if the gas was behaving ideally, then this ratio would be equal to 1, right? Because when the gas is behaving ideally, it satisfies the ideal gas law, and that's what this is, essentially. So the ideal limit would correspond to a value of Z equals 1. I'm going to rearrange this a little bit, and let's just call this pressure, we'll call that the real gas pressure, and then this Vm divided by RT, that's the ideal gas pressure. Okay, so here we have the ratio of the real gas pressure divided by the ideal gas pressure. Here you can compare it to see where my error is. I had it flipped around. I had the reciprocal of the correct definition. So let's use the paper as the correct definition, and then the words that are written here, the expressions and the words, these correspond to the correct equation. So as I was saying, if the real gas is behaving ideally, then the two pressures are the same, and Z equals 1. If you look at the diagram where we're plotting Z as a function of pressure, notice that these are very large pressures. So 200, 400, 1,000 times atmospheric pressure. This is a very large pressure. 1 atmosphere, where we live, is way over here. Okay? And you see that all of these different gases, they all have a compressibility factor that's near 1, which means that at low pressures, they're behaving ideally. Now, as you start to increase the pressure, so you're going to higher and higher pressures, you can compare the real gas pressure to what you would get for an ideal gas. And in the case where the real gas pressure is less than the ideal gas, okay, so the numerator is smaller than the denominator. So the pressures that you're measuring are less than what you would expect from an ideal gas. What you find is that Z will be less than 1. And so you see that all of these gases, as you increase the pressure, you see that that Z is less than 1, which means that the real gas pressure is less than what you think it should be. And let me try to explain that in terms of this picture. What it means is that, if the real gas pressure is less than the ideal gas pressure, that means that the molecules aren't hitting the wall quite as hard as they would if they were ideal. And the reason they wouldn't hit the wall as hard is if they were being pulled into the gas. So the way I think about it, for this case, where Z is less than 1, what it means is that the gas molecules are pulling in on themselves. They're attracted to one another. And so under these conditions here, the gas molecules are feeling their attractive interactions between each other. We also have, if you go to higher pressures, eventually you'll find that the compressibility factor goes back up, and what you get is the compressibility factor will be greater than 1. In that case, what you find is that the ideal, for the case where Z is greater than 1, you find that the ideal gas is less than the real gas pressure. So the numerator is then larger than the denominator. I think that's written incorrectly here, so I do have that. Yeah, these are the exact same expressions, so this expression here is wrong. So scratch that out. Here's the correct version. When the ideal gas pressure is less than the real gas pressure, this number is going to be larger than 1. That means that the real gas pressure is higher than you would expect for an ideal gas, and that means the molecules are hitting the wall harder than they normally would if they were ideal. That means, the way I think about it, it's like the gas molecules are trying to get away from each other, right? They're feeling a repulsive interaction and trying to hit the wall harder, trying to get out of the container to get away from each other. And so for the case where Z is greater than 1, that means that repulsive interactions are dominating the gas. Okay, so by measuring the compressibility factor for a real gas, you can say something about the nature of which interactions are dominant in that, for those particular conditions. Are the gas molecules attracted to each other on average, or are they repelled by each other on average? So that's one way to examine the deviations from ideal behavior, using the compressibility factor. Another way to describe real gases is to go beyond the ideal gas law and to come up with other gas laws. Okay, gas laws that correct for the shortcomings of the ideal gas law, namely to take into account a correction factor for the volume of molecules and for the attractive interactions between molecules. And there are many such equations of state that are designed to improve upon the ideal gas law. One of them is called the van der Waals equation. Okay, so the van der Waals equation is convenient. It has a similar form to the ideal gas law, but it takes into account real gas behavior. And so here is the form of it. It has a pressure term times a volume term equals number of moles times R times T. And so that's what I mean by it kind of looks like the ideal gas law. You've got a pressure thing times a volume thing equals nRT. As you can see, the pressure is modified. It's modified by a correction factor for attractive interactions. And then this part that's being subtracted from the volume takes into account the fact that molecules have a volume to them. They have a size. The parameters A and B are unique for a given gas. So different gas molecules will have different van der Waals parameters. And so there's really a separate equation for each different gas. And you can look these parameters up in tables for different gases. And I think what I just wanted to show you here is how to use the van der Waals equation. So we have a problem here. Let's go ahead and do the next one because it's a bit easier to understand. It just says, use the van der Waals equation to calculate the pressure of 1 mole of ethane that has a volume of 22.4 liters at 0 degrees Celsius, and compare that to the value that you would get for the ideal gas. Let's do the ideal gas first because it's easier. So P equals nRT over V. We've got 1 mole of gas. For the gas constant, we use 0.082081 liter atmospheres mole Kelvin. The temperature, what are we at? 0 degrees Celsius, so that's 273 Kelvin. And then the volume, 22.4 liters. And so we'll get this number real quick. And so that's 1 atmosphere. To do the van der Waals pressure, let me write down the van der Waals equation as we had it on the previous slide. We need to do a little bit of rearranging. Okay, so we're trying to find the pressure. So I'm going to divide both sides by this V minus NB. And now what I'm going to do is I'm going to move this term over to the other side. So this will be the van der Waals pressure. And make that look a little bit more like an N. And so now we've got, okay, so it's 1 mole times the gas constant. Then we've got the temperature. And then we need to divide by this 22.4 liters minus 1 mole times the value of B. So this is going to be 0.06499 liters per mole. Okay, so that's the first term. And then we need to do the second term, 1 mole again. Now we need to square that and then multiply by the value of A, 5.570 liters squared atmospheres per mole. And then in the denominator, we need the volume squared, 22.4 liters squared. Okay, so we'll calculate each term separately. 0.0821 times the temperature divided by the quantity 22.4 minus 0.06499. So for this first term, I'm getting 1.0035. That's going to be atmospheres minus 0.0111 atmospheres. Add those together. And you get 0.992 ATMs. So under these conditions, 0 degrees Celsius, and we're at roughly 1 atmosphere pressure, there's very little difference between the real gas behavior using the van der Waals equation and the ideal gas behavior using the ideal gas law. However, if you go to higher pressures, what you'll find is that there will be larger and larger deviations from ideal behavior. And so the van der Waals equation is just a way of taking that into account. It's a way of taking into account the interactions between molecules and the fact that you can't completely neglect molecular volume. Okay? But at low pressures, you really don't need to use the van der Waals equation. You can get away with the ideal gas equation. Well, I'm going to stop this video here, and we'll talk about the last chapter that we're going to cover, chapter 10, in the next video, liquids and solids.